In this lesson, we want to give an introduction to vectors, and specifically here we'll focus on finding the magnitude and also the direction angle. All right, so when we work with vectors, we're basically going to see this as a directed line segment, okay? So this is going to have what we call a magnitude or a length, and then also a direction, which is given by the arrowhead, okay? So if I look at this directed line segment with an initial point of O and a terminal point of P, you can see that it has a magnitude or a length, okay? And it also has a direction given by, again, the arrowhead. Now, the way you would notate this would vary by textbook, but I would take my initial point here of O, okay? And I would list that first. That tells me it's the initial point. Then I would take my terminal point P, and I would list that second, okay? That tells me that's the terminal point. So the order here when you're using two letters is going to matter, okay? And then I want to put a little arrow on top. Okay, so this is the typical way that you will see this notated. Now, you could also use a lowercase letter, okay, something like, let's say V, okay, something like that, and do the same thing, right? But this one is going to give you the information about, hey, O is the initial point and P is the terminal point. This guy just tells you have a vector, okay? Now, let's erase this for a moment. I want to show you a few other ways that you might see this notated. So in your book, you might see this, okay, where they just put that guy like that, okay? You also might see this listed with a bar on top. And then lastly, you might see them just use a boldface font, okay? So you might see them just do that. Now, I'm going to stick with this for this tutorial. In a few minutes, I'm going to start talking about the magnitude or the length of this guy, okay? And the notation for that is basically where we're going to use these vertical bars. So the magnitude of this vector OP, I could put it in vertical bars to show that. Or sometimes the textbook will use two vertical bars, okay? So go with whatever your textbook goes with. I'm going to use single bars here because that's what my textbook uses. Now, if we look at these two directed line segments or these two vectors, the first thing is if I'm using the two capital letters to name them, this guy would be named OP, okay, that vector OP. Here is going to be your initial point, and here's going to be your terminal point, right? So this guy would be the vector OP, like this. Now this guy is not going to be the vector OP, okay, because the initial point is here now, and the terminal point is here, right? These have different directions. Look at the way the arrowheads are facing, okay? This one is facing this way, this one is facing this way, okay? So different direction, same magnitude, but this one's going to be called PO, so this will be vector PO, okay? Let me get rid of this and make that a little bit better. Now, I can say right here that this vector OP is not equal to this vector PO. And the reason they're not equal is because for two vectors to be equal, they have to have the same magnitude or the same length, and also they have to have the same direction. These do not have the same direction, even though they do have the same length. So I can say this vector OP is not equal to this vector PO. All right, so now let's think a little bit about the magnitude and how we find that. Also something called the direction angle and then the component form, okay? So let me start with the component form because I think everything kind of builds off that. So first and foremost, you see on this sketch, the way this is drawn, we have our initial point at 0, 0, or the origin. Okay, so let me label this. This is 0, 0. Then we have our terminal point at this A, B, okay? So because this guy has an initial point at 0, 0, we call this a position vector, okay? Or we say it's in standard position. Now, when you have a position vector or when it's in standard position, you can just list the coordinates for the terminal point. That's all you need because you know the initial point is at the origin, okay? You don't need any more information. So the way we list this is called component form, okay? So here I've named my vector u. So the vector u is equal to, you'll see we have these angle brackets here, and we're just listing the A and the B. All this is the X and the Y, okay, from the ordered pair. We're just listing it inside of those angle brackets. So if I said that I had a vector u, okay, is equal to, let's say I had 3, 4, well, I know, and I didn't make those brackets very well, I know that the X location is 3 and the Y location is 4 in terms of the point, okay, the terminal point for that vector. So I would start with the initial point at 0, 0, and then I would draw a terminal point at 3, 4, okay, and I would just draw a directed line segment. That's all I'm doing, okay? So additionally, we also have something called, let me just erase all this. We don't need this anymore. We also have something called the magnitude of the vector, which we already talked about. It's the length of this guy, right? So if I said, what is the length of this guy right here? So if I just drew this line right here, what is the length of that? Well, again, normally if we form a right triangle, okay, we can do this with the distance formula. Let me just call this side C for a moment. So I'll say C, which is the hypotenuse typically, okay? So C, I'll say C squared is equal to this A squared plus B squared. So we know if we want C by itself, we say C is equal to the principal square root, we don't need the negative one, of A squared plus B squared, okay? Well, now instead of C, I just have the magnitude of U, so I'm just going to replace that, okay? That's all I'm doing. So the magnitude of U is just equal to the square root of A squared plus B squared. Now, in the case where you're not given a position vector, okay, you're going to either have to put it into component form or use your original distance formula, right? Remember, the distance is equal to, you have the square root of, you have the quantity x sub 2 minus x sub 1 squared, plus the quantity y sub 2 minus y sub 1 squared, okay? In this particular case, your point down here is 0, 0. So if you do this, it just becomes A, this is going to be A, right, for the x location, A minus 0, which is A, being squared, then plus, this would be B minus 0, okay? So it would be B just being squared, okay? So that's all it is. So let's get rid of this, and we see how to find the magnitude. Now let's talk about how to find the direction angle, because this one's quite confusing, okay? So basically, the direction angle is going to be this positive angle theta here between the x-axis, okay, and our position vector. Now, it turns out that it's pretty easy to find this overall, okay? All you really need to do is some basic trigonometry. In these problems, if you're given A and you're given B, so if you're given this and you're given this, and you're trying to find this angle here, what can you do? Well, remember the tangent is y over x, okay? In this case, it would be b over a. So the tangent, okay, of this angle theta is going to be equal to b over a, and you could say specifically where a does not equal 0, okay? But you're going to have to do more work than this because, again, if you involve the inverse tangent function, remember that guy is going to only return something from quadrants 1 or 4, okay? So you have to basically think about this by getting a reference angle in most cases and then figure out what quadrant you're in, so you're going to have to do a bit of detective work. Okay, let's go ahead and take a look at a simple problem. So I'm given a vector p, okay, and the component form gives me a horizontal component of -2 and a vertical component of -5. Okay, so if you wanted to sketch this guy, you would have one point at the origin, okay, at 0, 0, okay, that's your initial point, and then you'd have a terminal point at -2, -5. Let's just look at the graph real quick. So you see your initial point is here at 0, 0, okay, and your terminal point, you're going 2 units to the left and 5 units down, so it's at -2, -5, okay? It's just a directed line segment. That's all it is. So if we think about the magnitude of this guy, again, that's pretty simple. The magnitude of this vector p is going to be equal to the square root of, again, you're going to square each one and then sum the results. So I'd have -2 squared, okay, make sure you put in parentheses, then plus you'd have -5 squared, okay? So you want the negative and the 5 being squared and the negative and the 2 being squared. Make sure you use parentheses. Okay, so what I'm going to do here is I'm going to say that the magnitude of this vector p is going to be equal to the square root of, let's go ahead and say -2 squared is 4, okay? Plus, if you do -5 squared, that's 25. So that would be 4 plus 25 or 29, okay? So this is the magnitude of this vector p, okay? Nothing more than just the distance formula. Now, if we think about the direction angle, this is where things get a little bit more tricky. Let me get this out of the way, okay? If I go back, I want you to observe a few things, and I can just erase this. We're trying to find this angle theta here, okay? If we think about this, if we swing this around, we see that this guy is in quadrant 3, okay? So in quadrant 3, if we think about tangent, it's going to be positive, right? Remember this, all students take calculus, okay? But if I use my inverse tangent function, I'm not going to get something in quadrant 3. I'm going to get something in quadrant 1. So if I go back and I think about this guy, remember the tangent of theta is equal to, you take your y value or your vertical component, which is -5, over, you take your x value or your horizontal component, which is -2. And so basically I could say the tangent of theta is really equal to 5/2, right? So if you do the inverse tangent on this, so you do tangent inverse of this 5/2, you're going to get something, let's say it's approximately, I'll go with 68.2 degrees. Okay, so 68.2 degrees. And again, I'm just rounding. So if I know that this guy right here is the result of the inverse tangent function, well, again, if I'm in quadrant 3, this is not my angle. Okay, so people mess up all the time and say, okay, well, theta is going to be 68.2 degrees. That's wrong because I'm in quadrant 3. So if I go back, you can visualize what's going to have to happen here, okay? I've got to go 180 degrees first, okay? And then I also need to add on top of that reference angle to get the rest of the way, okay? So I need 180 degrees plus the reference angle to get this angle here, theta. So if I go back, all I want to do is say theta is going to be equal to 180 degrees plus 68.2 degrees. And you can put approximately here. Let's just leave the equals for a moment. I'll just go ahead and change it in the end. So this is going to be what? It's going to be 248.2 degrees, okay? So let me erase this. We don't need this anymore. So that's our direction angle. It can be a little bit confusing. Just make sure you understand what quadrant you're going to be in, and that when you're working with the inverse tangent function, you're getting something in quadrant 1 or 4 only, okay? So let's go ahead and put this as 248.2 degrees, okay? Also, I should note that if you get something in quadrant 4 from the inverse tangent function, remember, it rotates clockwise to get that, okay? So that's not going to be your angle either, okay? So you got to do a lot of detective work when you're doing these. Okay, so we found that the magnitude of our vector P is the square root of 29, and the direction angle is approximately 248.2 degrees. All right, let's look at another easy one, and then I'll show you something that's a little bit harder. So we have this vector V here, okay, and the horizontal component is -7, the vertical component is -6. So again, if I wanted to find the magnitude, so the magnitude of this vector V, this is equal to the square root of, you could say -7 squared plus -6 squared, okay, like this. So the magnitude of this vector V is equal to, let's go ahead and say this is 49 plus 36, so that's going to be 85 in here. So basically the square root of 85, really can't do anything to simplify that, so that's just going to be our answer, okay? Let's get rid of this, and let's just drag this up here. And again, finding the direction angle usually takes a little bit longer because you got to plug some stuff in. Now, if I think about this again, the tangent of theta is equal to, again, it's going to be the vertical component, -6, over the horizontal component, -7. Might as well just say this is 6/7. But again, if I do the tangent inverse of this guy right here, I'm going to end up with something in quadrant 1. Where is this guy at? If I graph it, again, my initial point is here at 0, 0. My terminal point, I go 7 units to the left and 6 units down. So it's at -7, -6, okay? So if I look at this guy, I'm going to be in quadrant 3, right? This is the angle theta that I'm trying to find. So I've got to swing all the way around here. So remember what we have to do. We've got to go 180 degrees and then plus that reference angle to get there. So let's go back and let's punch this into the calculator. And that's going to give us about 40.6 degrees, okay? So again, when you think about this, I'm going to say that my direction angle theta, I'll just put approximately here. I'll go 180 degrees plus I'll go 40.6 degrees, okay? So what is this going to give me? It's going to give me 220.6 degrees. So let me erase all of this. Let's just put our answer here. So 220.6 degrees. So again, the magnitude of this vector V is square root of 85. The direction angle is approximately 220.6 degrees. All right, let's take a look at another example. So this one involves a little bit more work. So we have this vector PQ, okay? So we know because of the way this is listed, right, from the beginning of the lesson, we said that the first letter here, P, is the initial point, right? So the coordinates are 2, -9. The second letter Q is the terminal point, so the coordinates 1, -4, okay? Let's go ahead and sketch this real quick. So if we look at this guy, we go 2 units to the right and 9 units down, so that's right here. This is going to be your P, or your initial point. Again, this is 2, -9. And then the other one here, if we go 1 unit to the right and 4 units down, we're going to be right there. So that's going to be Q, okay? That's our terminal point. So again, this is 1, -4. So the first thing you want to do if you have a problem like this, you want to put it in the component form. Again, this is where the coordinates for the terminal point are given only because the initial point is at 0, 0, or the origin, okay? So you'll see that I already have this graphed, right? So this is 0, 0, or the initial point. And then you'll see the terminal point is at -1, 5. So where does this come from? How did I get that? Well, if you go back here, it's a simple little formula. All you really want to do, let me come over here, and say for this vector PQ, okay, and sometimes books will rename this with a lowercase letter once it's in component form. That's up to you if you want to do that, okay? I'm going to keep it as it is. So I'm going to say this is equal to, I'm going to put my little angle brackets there, And basically to get this position here, you go with the x value from your terminal point. Okay, so I'm going to take this 1 right here, okay? And then I'm going to subtract away the x value from your initial point, so minus 2, okay? So 1 minus 2 gives us negative 1. Now, you want to go in that order. I know sometimes when you work with these formulas, if you reverse them, they come out fine. But in this case, you want to go from the terminal point, okay? You want to start with that and then subtract away from the initial point, okay? So the same thing with x's and y's. So with this guy, I'm going to take this one minus this one, okay? This is from the terminal. This is from the initial. So I want to go negative 4 minus a negative 9, which is negative 4 plus 9, which equals 5. Okay, so that's where that terminal point of negative 1 comma 5 came from. If you go back, you see this is 1 unit to the left and 5 units up. So this is negative 1 comma 5. And you can call this the point Q. Okay, now the point P is at the origin. Okay, and because of this, a lot of books, again, will just rename this as the vector V or U or whatever they want to do. I'm just going to keep it like this. Now, if you want to find the magnitude, okay, and make another little border here, of this vector PQ, okay, what I'm going to do is just take the square root of, I'll take this first guy, negative 1 squared, plus the second guy, 5 being squared. Okay, so the magnitude of PQ, okay, like this, is going to be the square root of negative 1 squared is 1, plus 5 squared is 25, so this can be 26. So it's just the square root of 26. Now, if you wanted to come over here and use these points, again, you could plug into the traditional distance formula. You could say, and I'm just going to label this as the magnitude of this PQ guy. Okay, I'll show you it's the same. Basically, you're going to subtract this guy minus this guy. So x sub 2 minus x sub 1. So it's going to be 1 minus 2. Let me write this out. So 1 minus 2, this is squared. Then plus, you're going to do this guy, that minus this guy. So negative 4 minus a negative 9 is plus 9. Okay, this is going to be squared. And we want the square root of this guy. Okay, so notice that we already did this to find these guys right here. Okay, so we're a step ahead. Right, so that's why we do this first, and then we don't have to do all this, okay? So 1 minus 2 is going to be negative 1, so it's negative 1 squared, which you know is 1. And then negative 4 plus 9 is 5. 5 squared is 25. So this becomes square root of 26, okay? Just like it is over here. Okay, so you see it's the same magnitude in each case. Now, let's talk a little bit about the direction angle. So theta, this is what? Well, again, let me actually erase this. Let me just say that the inverse tangent, I think we can kind of skip ahead a bit. The inverse tangent of what? Well, I'm going to take the vertical component, which is 5, over the horizontal component, which is negative 1, which really I could just write as negative 5, okay, like this. Now, when you talk about putting a negative as the argument for this inverse tangent function, you're going to get something in quadrant 4, okay? So in this particular case, if we think about this, this horizontal component is negative, this vertical component is positive. If I think about it, where am I going to be? I'm going to the left and I'm going up. So I'm going to be in quadrant 2. If you want to see this graphed on its own, you'll see, again, my terminal point here is that we go 1 unit to the left and we go 5 units up. And you see I'm in quadrant 2 here, okay? So basically, when I do my inverse tangent function, I'm going to end up with something in quadrant 4, and also I'm going to be rotating clockwise, okay? So I want to just take the absolute value of that and think about that as my reference angle. And then what I want to do, in this particular case, I would think about the fact that, okay, if I had an angle of 180 degrees, I want to subtract off and go back by the amount of the reference angle, right? So I want 180 degrees minus the reference angle to get this angle theta here, okay, this angle theta here. Now, let's go back. So I'm going to get about negative 78 point, let's say 69. So let me kind of slide this down because I don't think it's going to fit. So I'll put it's approximately negative 78.69 degrees. Now again, what I want to do is I want to think about this in terms of absolute value. So in quadrant 2, I want an angle with a reference angle of 78.69 degrees. So all I'm going to do, get rid of the negative sign, I'm going to say theta is approximately 180 degrees minus this 78.69 degrees. And that's going to be about 101.31 degrees. So let's just erase this and put it's about, or approximately, 101.31 degrees. All right, for the last two examples, we're basically going to reverse things. So now we're going to be given the magnitude of the given vector, and we're also going to be given the direction angle, and we have to come up with the component form, okay? So let's think a little bit about this angle theta, and let's think about if I had this guy B and I had this guy A, well, let's think about some relationships here. I know that the sine of this angle theta is opposite, okay, over the hypotenuse, which in this case would be the magnitude of this vector u. okay? So I can say that the sine of this angle theta is equal to, we'll go ahead and say this b here, which is the vertical component, over the magnitude of this vector u, okay? So I'm going to be given the angle theta, and I'm going to be given the magnitude of this vector u, so I should be able to plug in there and figure out what b is, okay? Then also if I think about the cosine, so the cosine of theta, what is that? Well, that's now adjacent, so let me erase this. That's the adjacent over the hypotenuse. So this would be a over the magnitude of this u guy, okay? So we can use these two. We'll just basically solve them for a and b, okay? And then we'll plug in and we'll have our answers. So let me just paste this in here, and let me drag this over a little bit. We can solve this for a and b to come up with a nice little formula to use here. So basically, if I multiply both sides here by the magnitude of this vector u, you're going to see that b is equal to, you would have the magnitude of this vector u, and then times the sine of this direction angle theta, okay? Then here, a is equal to the magnitude of this vector u times the cosine of theta, okay? Let's get rid of this. Now we have a little formula to use. So I'm given the magnitude of some vector n, okay? So I want to find the component form. And basically, all I'm going to do is think about this and this. So I want the a and the b. So the a goes here, the b goes here, okay? That's all we're doing. So the first one for the a, you're going to think about going down here. The magnitude, in this case, of our vector n is 27. So I'm going to have 27, let's put a equals this, so 27 times the cosine of the direction angle, theta, in this case is 300 degrees. Now first off, a 300 degree angle is in quadrant 4. Cosine is positive in quadrants 1 and 4, okay? So we know that this guy's going to be positive. Now 300 degrees has a reference angle of 60 degrees, and cosine of 60 degrees is going to be a half. So I can just put times a half here, and this is basically 27 over 2, okay? So 27 over 2, okay? And then for b, it's equal to what? So in this case, again, the magnitude of this vector n is 27, and times the sine of this guy, 300 degrees. So again, think about the fact that in quadrant 4, your sine is going to be negative, right? Sine is positive in quadrants 1 and 2 only. So in quadrant 4, it's going to be negative, okay? So I'm going to put negative, and then the reference angle is 60 degrees. So sine of 60 degrees is square root of 3 over 2, okay? So all this is, you're not going to be able to really simplify this too much. You're going to say this is negative, let me put this out in front. So the negative of 27 times the square root of 3 over 2. Let me close my brackets down. So this would be your component form for this vector n. Let's look at one more of these. So again, all I'm going to do here, let's go ahead and write this vector k like this, is equal to, I'm going to set up my brackets, and again, this is a comma b. So a is equal to, again, with the horizontal, you're thinking about cosine, right? So all it is this guy right here times the cosine of this right here. So 32 times the cosine of 120 degrees. Now this again has a 60 degree reference angle, but now I'm in quadrant 2 and cosine is negative in quadrant 2. So this is going to be negative half, right? So negative 1/2. So this will end up being negative 16, right? So if we put this in here as negative 16, because this will cancel with this and give you 16, okay? And obviously this is times negative 1, so that's where the negative comes from. Okay, let's get rid of this. Let's think about b now. So b is equal to, you're going to take the same 32, the magnitude of this vector k, times now the sine, okay, the sine of this 120 degrees. Well, I'm in quadrant 2, okay? I have that same 60 degree reference angle, but now sine is positive, okay? So this is going to be times square root of 3 over 2. And so this is going to cancel with this and give me 16. So this is 16 times the square root of 3, okay? So 16 times the square root of 3. So that's going to be our component form, and maybe I should make that 3 a little bit better, okay? For this vector k, again, your horizontal component is negative 16. Your vertical component is 16 times the square root of 3,